Hello everyone, this is Chandrakant Mishra. Today we are going to discuss the network theorems. Network theorems are backbone of electrical network analysis. Here we will discuss the LTI networks, linear time invariant network. Linear means your voltage proportional to the current or voltage proportional to the derivative of the current or voltage proportional to the integration of the current. All these categories comes under the linear. And time invariant, these equations remain valid whenever you perform the experiment repeatedly, today, after 1 month, after 6 months, after 1 year, after 2 years, every times these equations will be valid. In simple terms, you can say the behavior or response of a network remains unchanged regardless of the time when you perform the experiment. For example, suppose you have a battery, you have a resistors, you have a capacitors. Let's say you have a switch here. This is the voltage. Nature of current will be remains unchanged when this switch is closed. Whether you close the switch just now, or after 1 month, or after 1 year. First one, we'll discuss the superposition theorem. The most important consequence of linearity is superpositions. We all have linear networks, so you can apply the superposition theorem. The theorem states that in any linear network, the response of network at any branch of the network may be calculated by considering each independent source separately, leaving their internal impedances and adding algebraically individual responses. Linear dependent sources are active in every experiment. Independent voltage source replaced by short circuit, independent current source replaced by open circuit. So it will be better explained with the example. We need to find the current I. So we use the superposition theorem. We will consider each source separately. Let us consider source 6 volt alone. So we are considering only 6 volt as it is a ideal current source. It will be replaced by open circuit. So this current I due to voltage source alone is 6 upon 3 plus 6, that is 6 upon 9, that is your 2/3 ampere. Now consider another case, that is keeping only current source in the network. So as you know that ideal voltage source will be replaced by a short circuit. We need to find the current due to the current source. Current division relations. So you can find 3 upon 3 plus 6 into 2, that is 6 upon 9 again. So 2/3 ampere. So total current you have to add algebraically. So I equal to II plus IV. So you will get 2/3 plus 2/3, which is 4/3 ampere. Consider this example. Here we have 2 independent source and 1 dependent source. You will not disturb the dependent source. So only you have to consider independent source separately, like 24 volt and 7 amperes source. So first we will consider the 24 volt source alone. Because it's the ideal current source, it will be open. IV because we are considering only voltage source. See, every time you will not change the reference current, associated current in the dependent voltage source. So here the current was I, so 3I. So here current is IV and so 3IV. KVL around because only one loop is here, so KVL. So you will get 3IV plus, because 3 ohm 2 ohm, that is 5 IV, which is 24. So you will get IV current due to the voltage source 24 upon 8, that is 3 ampere. Now second case, we will have the voltage source will be shorted and we will have only current source. You will have your 7 plus II is current. So put a KVL here. So 3 II plus 2 into 7 plus II, then plus 3 II equal to 0, 8 II equal to minus 14, which gives you II is equal to minus 14 upon 8, which is minus 7 upon 4. You have to find the total current. So total current I is equal to I due to the only voltage source, I due to the only current source. We are adding algebraically, remember it, 3 and then II minus 7 by 4, which is 5 upon 4, which is 1.25 ampere. Next we will discuss the source transformations. The voltage source with a source resistance Rs can equivalently be transformed into a current source and a shunt impedance. So current source will be the simply Vs upon Rs and the shunt impedance is your Rs. This is called the source transformations. Equivalently, you can also write like this from the current source to the voltage source. Is, then Rp, do this to a voltage source and a series resistance or series impedance, and this Vs is equal to Is into Rp. So let us discuss with an example. In this example, we need to calculate the value of Ix. We need to calculate the Ix, so we need not to disturb this source. So only we can do this source transformation with a current source. So as you know that the current source will be the 10 upon 5 kilo, that is 2 milliampere, and then a shunt resistance of 5 kilo. Then you have the circuit other element, which is, this is 10 kilo, and then right 1 milliampere. So see here 2 milliamperes and 1 milliamperes flows in the same directions. I can club together 5 kilo, 10 kilo. When I club this current together, I will have net current of 3 milliampere, and this is your current Ix. You need to calculate through the 10 kilo ohm. So Ix will be the, due to the current divisions, so 5 kilo upon 5 plus 10, that is 15 kilo, into the 3 milliampere, that is 1 milliampere. Next we will discuss the Thevenin's theorem. This is an important theorem. A linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH and a series impedance ZTH, where VTH is the open circuit voltage at the terminals and ZTH is the impedance of the network look back from terminal. Independent energy sources replaced by their internal impedances and dependent sources are operating. A linear networks at the terminal AB can be represented the VTH is the open circuit voltage. Here measure this voltage, this will be your VTH, and ZTH is the impedance look back from this terminal A and B towards the network by replacing the independent source with their internal impedances and dependent source operating. Let us move to the example to have complete understanding of the theorem. Find the Thevenin equivalent circuit at AB and find the current through 2 ohm resistors. We need to find the Thevenin's equivalent at A and B and then find the current through this. First of all, you will cut here. Once you cut here, you will find that this circuit will be like this. So what is this open circuit voltage? VTH is equal to, as this terminal is open, no current flows through the 4 ohm resistors, and whatever the voltage drop across the 20 ohm resistor is same as the VTH. Here you have 50 volt. So by potential division, 25 plus 20 into 50, which is equal to 40 volt. This is your VTH. Now you will find the ZTH. As per the theorem, you have to sort the voltage source. Then this is your A and B, and this is your ZTH. That is Thevenin impedance is the impedance looking back from the terminal AB. ZTH is equal to 5 parallel 20 plus 4 ohm. So 5 parallel 20 is exactly 4 ohm, then 4, that is 8 ohm. We got this VTH, ZTH, 8 ohm, and this is your 40 volt. Then you connect your load, that is your RL 2 ohm. So this is your current, your IL. So it is easy. So IL is equal to 40 upon 2 plus 8, that is 40 upon 10, that is 4 ampere. Procedure for finding Thevenin impedance. First procedures we have just now seen, where we have only independent sources, so you can replace with the equivalent circuit and find the ZTH. Another case, you can also find ZTH as open circuit voltage and short circuit current. What is the short circuit current? This is network. We have found the open circuit voltage or Thevenin voltage. This is open circuit voltage. How to find the short circuit current? This is A and B. So short circuit current, this is terminal A, terminal B, put a short, and this is your short circuit current. By dividing the open circuit voltage upon short circuit current, you can find the ZTH. Another procedure, you can also drive the networks with a voltage source. Networks mean linear network. You can drive the terminal A and B, connect a voltage source of V2. So obviously the current will be I2. In this case, you have to replace the independent sources with their internal impedances, right? And dependent source, if any, they will be operating in the network. So your ZTH will be the V2 upon I2. Is the part A, and part B can be like driving the network. What do we do usually? Drive with a current source. This is the easiest way, 1 ampere, and measure this voltage V, and your ZTH is numerically equal to V, because V upon 1 ampere same as V. Let us move to the example. Find Thevenin's equivalent circuits at terminal A, B. 20 volt source, 6 ohm, 2I, 6 ohm, 10 ohm. So first of all, we'll find the Thevenin voltage here, VTH. So using the KVL, 6I minus 2I, then plus 6I minus 20 equal to 0, which implies 10I equal to 20, which implies I equal to 20 upon 10, 2 ampere. So your VTH will be the, you can find out this way. This is your VTH, because no current here 0. So your VTH will be the 6 into 2, 12 volt. Now come to the RTH. I have connected a current source of 1 ampere. I have sorted the voltage source here, and so this current will be the 1 minus I. Using the KVL in this loop, first loop, 6 of I minus 2I minus 6 into 1 minus I equal to 0. So you have 10 of I equal to 6, I equal to 0.6. So your V will be the 6 into I plus 10 into 1. So 6 into 0.6 plus 10. So ultimately 13.6 ohm. So we have VTH, or open circuit voltage, 12 volt, and ZTH is equal to 13.6 ohm. Next, Norton's theorem. Norton's theorem states that a linear two-terminal networks can be replaced by an equivalent circuit consisting of a current source IN in parallel with the impedance ZN, where IN is the short circuit current through the terminals and ZN is the impedance looking into the networks from the terminals. It is same as calculated in case of Thevenin's theorem. So only difference is the we need to find the short circuit current in this Norton's theorem. So here the linear networks, terminal A and B. So what you will do, you will short this terminal and measure the current. That is your current IN. And impedance is same as the Thevenin impedance, looking back from the terminal to the network, and equivalently you show it IN and the Zn. Let us go through an example. So we have networks, 24 volt voltage source, 4 ohm, 3 ampere current source, 12 ohm terminal A and V. We need to notarize these circuits. Put a short here, measure this current, and this is your IN. When you put the short here, that means potential here, let's say V, and potentially here same, so no current flows through it, right? So your IN will be this 3 amperes and 24 upon 4, that 6 amperes. So the IN will be the 3 plus 24 upon 4, 9 ampere, and Zn equal to, so this is your Zn, so 4 ohm parallel 12 ohm, that is 48 upon, so 16, 48 upon 16, that is 3 ohm. So you can represent equivalently 9 ampere, and this is your 3 ohm. You should always remember that Norton and Thevenins are dual of each other. If you have been given the Thevenin values, by source transformation you can find the Norton's values. So this Norton's current will be, the IN will be the VTH upon RTH, and this is RN is equal to RTH. And similarly, if you have been given Norton's values, you can find the Thevenin's values by source transform. Many times it will be very handy for circuit analysis. Next we will discuss the reciprocity theorem. It states that in a linear bilateral single source circuit, the ratio of excitation to response is same when the position of excitation and response are interchanged. So you can see the linear bilateral networks. We have connected a voltage source V1 and we measure the current here, that is I2. Scenario 1. And in scenario 2, same networks, I just interchange the position of the voltage source and measurement of the current. So I take the voltage source or connect the voltage source at the terminal 2 and 2 dash and measure the current at terminal 1 and 1 dash. So according to the reciprocity theorem, V1 upon I2 scenario 1 is same as the scenario 2 ratio V2 upon I1. Okay, so condition to be met for application of reciprocity theorem. Circuit must have a single source. Initial conditions are assumed to be 0 in the circuit elements. Dependent sources are excluded even if they are linear. All passive networks are bilateral, hence reciprocal. Next, Telgen's theorem. It is applicable for all type of network. It says that total power delivered is always equal to total power consumed in a networks. That is summation all power is equal to 0, or same way you can write summation Vi equal to 0. And for AC circuit you will be writing like this, summation Vi I complex conjugate, because they are represented in phasor form, will be 0. Next we will discuss the maximum power transfer. It is very important theorem as far as competitive exam is concerned. First we will discuss the case 1, where variable resistors is connected in parallel with the another element. What is the values of R1 so that maximum power will be delivered to the load? So obviously only one case the maximum power will be delivered, that is when we short this or we make R1 equal to 0. Next case, here we have a source impedance which is represented by Rs plus Jxs, and we have a load impedance which is represented by RL plus Jxl. Always remember, we cannot modify the source impedance because source impedance is fixed to the source Vs. So we cannot modify, but we can modify our load impedance. That means we can vary RL and XL. So I becomes Vs upon J XS plus XL. So load power by definitions magnitude of I square into RL, which is V square Vs square XS into RL. For maximum power transfer, so your dPL with respect to dRL, because we are varying RL, okay. In fact, we have two variables, so we do the partial differentiation. dPL upon dRL should equal to 0, and del PL upon del XL equal to 0. If you differentiate these equations, you will have here, after manipulations, you will find that RL is equal to XL plus XS square plus RS square root. And from these equations, you will have XL equal to minus XS. If you combine equation 1 and equation 2, just put these values here. So you'll find that RL equal to RS and XL equal to minus XS. So if both the RL and XLs are variable, you can find that for maximum power transfer, ZL is equal to ZS conjugate. Clear? That is, for maximum power transfer, load impedance is the complex conjugate of source impedance. If RL is only varied, last case was both RL and XLs are varied. Suppose the case is the RL variable like this. In this case, we have already found. So RL is equal to XS plus XL square plus RS square. Another case, if XL is only varied, you cannot vary RL, but you can vary only. So in this case, you have already calculated XL equal to minus XS. A special case when XL equal to 0. That means load impedance is simple a resistance. In this case, your RL from equation 1, you can find your RL is equal to magnitude of ZS. When both are variable, so you have ZL equal to complex conjugate of ZS, which is RS minus JXS. So your I will be the VS upon 2 RS, right? And maximum power is equal to I square into RS. So VS square 4 RS, and you can find the efficiency is the power delivered to the load and total power delivered by source. You can simply find out VS square upon 4 RS upon VS square upon 2R. In fact, you can take the magnitude of all these terms, because the phasor, when we square it's we take the magnitude, and you will get the 0.5 or 50%. Next case of maximum power transfer is the transfer of maximum power from circuit 1 to circuit 2. Let the power is being delivered from the circuit 1 to the circuit 2. We need to optimum value of R so that maximum power transferred from circuit 1 to circuit 2. The procedure is straightforward. First of all, find the current, then find the power, because we need to minimize this R, find the optimum value. So dP upon dR equal to 0. From this you will find the values R. Then after finding the values R, if they have asked maximum power delivered to the circuit, you can put these values of R and find the values of power. Next, for DC, before we are considering the AC circuits. So now for DC, transferred when RL equal to source resistance, that is load resistance is equal to source resistance. And the most common form of the questions appears in the exams are they'll tell a circuits and they will connect a ZL or RL. Okay, so what is the values of RL, or what is the maximum power transferred to the load? So simplest way is the find the Thevenin resistance here, that is RTH. For maximum power transfer, you are doing a Thevenizing these networks. If it is AC, so ZL for maximum power transfer, ZTH complex conjugate. If it is a DC circuit, so RL will be the RTH. We will consider this example. Find the value of RL for maximum power transfer. What is this maximum power? So if we need to find the RL maximum power transfer, and what is the P max? This is a gate questions. So first of all, what will be the RL? So RL will be the, you will find the Thevenin's disconnect here, and you will find the Thevenin resistance. So all are independent source. This will be act as a short, this will be short, then this will be open. RL is equal to RTH for maximum power transfer. So 10 parallel 10, that is 5 plus this 10 ohm. Now next is the, you need to find the maximum power. So to finding the maximum power, you should first find the Thevenin voltage VTH. So Thevenin voltage is the, here same circuit I am doing, let's it is V and this is your VTH. So use the KCL here, 5 minus V upon 10. So 5 minus V upon 10 is equal to V minus 2, because here 2 volt, here V minus 2 upon 10 plus already you have a 1 up, which implies 5 7 minus 10 minus 3, and V is equal to minus 3 upon 2, which is equal to minus 1.5 volt. So what will be the VTH? VTH will be the V minus 10 into I. So you have minus 11.5 volt. So now you have minus 11.5 volt and your load 15 ohm. So P max is your V square upon 4R. So 11.5 square upon 4 into, you will get 2.2 watt. We will discuss the gate questions. These questions appear in instrumentation branch this year. In the given circuit, superposition is applied. When V2 is set to 0 volt, the current I2 is minus 6 ampere. When V1 is set to 0 volt, the current I1 is plus 6 ampere. Current I3 in ampere when both sources are applied will be: case 1, V2 equal to 0. So we have I2 equal to minus 6 ampere. You see the directions. V2 0 this case, so this 6 ohm and 2 ohm are in parallel. I2 is equal to minus of I1, because if this is I1, so this current will be minus of I1. Minus of I1, 6 upon 6 plus 2, and your I3 will be the minus of I1, 2 upon 6 plus 2 due to the current division. So what is this ratio? I3 upon I2 is equal to 2 upon 6. So it gives you the I3 equal to 1 upon 3 I2, and I2 is minus 6 ampere. So minus 6 upon 3, that is minus 2 ampere. This is the case V2 equal to. Next case, when V1 equal to 0. In that case, your I1 is equal to 6 ampere. Using the same ratio, in this case, I3 upon I1 is equal to just opposite their resistance they facing, that is 3 upon 6, that is half, which will give you I3 is equal to I1 upon 2, and I1 is 6 upon 2, that is 3 ampere. So total current I3 when both the source V1 and V2 are operating, you have to add the individual current algebraically. So minus 2 plus 3, which is 1 ampere. So this is your required answer. Next we will discuss the GATE 2017 EC questions. The Thevenin's equivalent resistance in ohm across PQ is. So as you know that to find the Thevenin resistance across PQ, you have to sort this because it is a independent voltage source, there is no current flows through this, right? Connect a current source of 1 ampere. We are following proper procedure. Measure your V. So your ZTH is equal to V, right? Numerically. Let this current be I1 minus I minus I0, right? And here you will have current 1 minus I0. Appropriate KVL. First of all, I will apply the KVL here, this loop. The KVL gives 1 ohm into I minus 3I0 equal to 0. I equal to plus 3I0. Now next is your through this loop. 1 into 1 minus I0. This is short. Then plus 1 into I, then minus 1 into I0 is equal to 0 around this loop. So it gives you 1 minus I0 plus I minus I0 equal to 0. So 2I0 equal to 1 plus I. We have to eliminate I. So I is equal to 3I0. So 2I0 is equal to 1 plus 3I0. It gives you the I0 is equal to minus 1 ampere, right? So now find the V. So V you will get 1 into I0, which is 1 into minus 1, which is minus 1. That means your RTH is numerically equal to V, which is minus 1 ohm. This is the answer. Next, consider the GATE 2017 electrical questions. In the circuit shown below, the maximum power transfer to the resistor R is in dash watt. So here is the R. So the question of maximum power transfer, so got it. You need to find Thevenin voltage here and Thevenin resistance. Then R is equal to, for maximum power transfer, you know that it is a DC circuit. So RTH equal to R for maximum power transfer. So RTH will be, see, you are cutting this. So in this terminal, you will find the RTH. So this will be your short. So ultimately what you will have the circuit, this is your 5 ohm. Let I designate A and B here. 5 ohm, and you know this is short. So short as it is. Then another 5 ohm here. So this is your A and B. So what you see here, 5 ohm and 5 ohm are in parallel. So your RTH is equal to 5 parallel 5, that is 2.5 ohm. This is the value of R for maximum power transfer. Next is to calculate Thevenin voltage across A and. So it is a straightforward things. You need to convert into a voltage source. What happens here? I'll again write. Here is a voltage source of 6 volt, then 3 ohm into a source transformation. So 5 ohm, and see the polarity of this voltage transform, because current flowing through these directions. So this will be positive and top one will be negative. So it will be 10 volt, and this is your AB. Let it, the current flows here I. So same current will be I. Put a KVL here. Minus 10 equal to 5I. Here minus 6 volt plus 5I, then minus 5 volt equal to 0. Then you have 10I is equal to 21. So your I equal to 2.1 ampere. This voltage VTH, simple application of KVL, VTH equal to 5 minus 5 into 2.1, which will give you 5 minus 10.5, which is minus 5.5 volt. Minus 5.5 volt, we have 2.5 and 2.5 ohm. So we need to find the power across this resistor. So you will have current I equal to, the current is, so I equal to minus 5.5 upon 2.5 and 2.5, that is 5, minus 1.1 ampere. So your power, maximum power, 2.5 into magnitude of I square, that is 2.5 into 1.21, which will be 3.025.